I want to just extend a warm welcome to everyone today that is joining us in our webinar. My name is Alex Semino-Hurt. I'm the Assistant Director of the Upper-West Onsite Energy TAP. I'm really excited to bring this webinar to you today on how industrial sites can benefit from solar and battery energy storage systems. And I'm excited to introduce the two experts we brought on our call today, Rachel Mountain and Drew Lebowitz. Rachel Mountain comes to us from Namaste Solar, which is a solar organization and company based out of Denver, Colorado. Rachel obtained a BA in Environmental Science Studies from the University of Tennessee, Knoxville, my neck of the woods, and kicked off her renewable energy career with an internship analyzing the feasibility of wind energy across the South. Since then, she joined Namaste Solar in 2017 and has since focused on a behind-the-meter commercial and industrial solar development across Colorado's Front Range. She is experienced with all aspects of project development, including initial feasibility, preliminary design, financial modeling, and contract negotiation. So Rachel currently serves on the board of Namaste Solar, the Colorado Solar and Storage Association, and the Colorado New Energy Improvement District. So thank you for joining us. Our other expert today is Drew Lebowitz, who comes to us from PowerSwitch, which is based in Portland, Oregon. Drew is an expert on lithium-ion battery energy storage systems, author of the BESS book, A Cell-to-Grid Guide to Utility-Scale Battery Energy Storage Systems. At PowerSwitch, Drew has provided advisory services on the design, construction, and management of over 3 gigawatt hours of utility-scale battery projects. PowerSwitch provides services to some of the world's leading projects, products, and players. So thank you so much. And next, what we're going to do is we're going to talk a little bit about the on-site energy program that's hosting this. So as I said earlier, I'm the Assistant Director of the Upper-West Onsite Energy TAP. For those of you who are not familiar with the On-Site Energy TAP program, they are a technical assistance partnership that is offered by the U.S. Department of Energy that really helps and provides the technical assistance to industrial end users and some large end users to explore on-site energy technologies for their site and figure out what might work for their site. As you can see in this slide, there are a number of technologies that we can evaluate for your site, and our work spans a broad range of different topics. The on-site energy TAPs, they cover the entire United States. So for folks that are joining this call that aren't in the Upper West, which is North Dakota, South Dakota, Montana, Wyoming, Utah, and Colorado, you can still get access to a TAP in wherever region you are in the United States. And our TAPs, we provide 3 main things: technical assistance in the form of a site-specific technology screening that you can have that's entirely DOE funded. End user engagement, for example, these educational webinars that we provide where we bring experts to you. And then also stakeholder engagement, where we're reaching out to a lot of the stakeholders in the on-site energy space and collaborating with them to connect with you to provide this resource. So without further ado, I'd like to hand it over to Rachel Mountain to start our portion of the talk discussing how PV can benefit industrial sites.
Thank you, Alex. Hello, everyone. Thank you for being here today. Just give me a brief moment while I look to take control of the slides. Excellent. So I'm going to start my part of the session with some high-level technical feasibility, but where I really want to spend the most time is going to be on the financial benefits and walking through the economics of a real project that we designed and built here in Denver. So as you all know, most industrial facilities are short, maybe 1 to 2 stories high, and this is advantageous for mobilization costs, including craning, as well as roof access during the installation and for long-term maintenance. Also, because these are often short, wide buildings, there's a lot of roof space available for solar, as you can see in this photo. And our systems don't fly over rooftop units, but rather we work around them and we take into account shading impacts and code required setbacks. And so a large industrial property is going to allow for a lot more roof solar than, say, a tall office building with a small footprint where most of the rooftop equipment is going to take up much of the roof space. I also want to point out that solar systems aren't just panels on the roof, so they do require additional equipment to make a complete system. That can include a number of things like inverters, transformers, switchgear, disconnects, and more. And those units have to be located somewhere. Oftentimes, they're ground level nearby the utility transformer and meter. And in a large, wide building like this one, there's a lot of exterior space to be able to accommodate that gear. So today we're going to focus mostly on rooftop systems, but I do just want to point out there are other common system types. Carports are becoming increasingly popular. Those are going to be raised structures with solar that cover parking lots. They are quite a bit more expensive than a rooftop system just due to a number of factors, most notably the custom engineered and fabricated steel, but they do provide added value through protecting cars from weather, which is especially great here in Colorado where we have lots of hail, and they're also highly visible. Ground mounts are also common, but more so for off-site systems as industrial and other facilities don't usually have as much land space available as they do on-site roof space. And then lastly, I want to note the utility rules. So the utility company that your facility is located in is going to have its own rules about what you are and are not allowed to interconnect at your site. And so we're going to talk a little bit more about the implications in a coming slide, but it is prudent to work with a contractor who has experience with your utility and understands their unique rules. So now I'm going to switch over and walk through the benefits of solar, starting with the four major financial benefits. First, there are tax credits available for investors of a commercial solar system. There's a base 30% federal investment tax credit, or ITC, which amounts to 30% of the system's eligible costs, and that's a one-to-one reduction in your tax liability. On top of that, with the passing of the Inflation Reduction Act in 2022, there is the addition of bonus tax credit adders if your project meets additional qualifying factors. So you can receive an additional 10% if your project is located in a federally designated energy community, which is typically an area with a coal plant closure. There's another possibility for 10% if it's located in a low-income community, another 10 to 20% if it's an economic benefit project. In my experience, I'm most commonly seeing these as affordable housing developments that provide some of the solar's value to its low-income tenants, so it is probably less relevant to the industrial group I'm speaking with today. And just a note, with the economic benefit and the low-income community adders, those two are capped. And so there is a max amount that the federal government will provide, so it's not guaranteed like the other tax credits. And then lastly, there's an additional 10% for using enough domestic content. So all these credits are stackable. They can be claimed for the year the system is placed in service or turned on. And then lastly, I just want to point out that for systems larger than a megawatt AC, you're required to meet additional labor provisions if you want to make sure you get the full amount of the tax credits. And just to quickly explain megawatt AC for this group here, this is just one way to refer to a system size. So AC is going to refer to the inverter capacity, so the number of inverters times their kilowatt rating. If we translate that to roof size, just for easier comprehension, that's about 175,000 square foot roof. And so labor provisions for these larger projects are going to include your contractor paying prevailing wages, meeting higher ratios for licensed electricians to apprentices on the job, and being able to properly record and report that information. If your contractor doesn't meet those labor requirements, then you only qualify for a 6% base tax credit instead of 30%. And so that would certainly have a pretty big impact on your return. So those are the tax credits. There is another tax benefit, which is bonus depreciation. So it's not a credit, but it's rather a deduction, which reduces the amount on which you are taxed. The basis is the total system price minus half of the ITC, and then the value to you will be that basis times your effective tax rate, as that is the amount that you would have avoided paying. Solar in particular qualifies for bonus depreciation, meaning that you can depreciate a greater amount in year one. And then as you can see in this chart here, that allowance steps down annually until 2027. So both the tax credit and depreciation amount to a minimum of 51% of your investment, much of which is recouped in year one. And that 51% can go higher just depending on how many of those tax credits you qualify for, as well as your effective tax rate. So the remaining financial benefits typically come over time as the system is producing electricity. So a reduction in your operating expenses through utility savings is generated because every kilowatt hour produced by your system is one less that you have to buy from the utility. And going back to my previous note on utility rules, some will allow for net metering, which means you can self-consume your solar production and also receive a one-to-one retail credit for any solar production exported to the grid. And that often happens in higher producing summer months. Other utilities, however, will allow you to self-consume, but will only pay their avoided cost for any exported energy. And so it's really critical, again, that you're working with a contractor who understands your utilities rules and they can properly model that in the financial case for your project. I also want to point out that if you're a property owner with a triple net lease, by nature of the fact that the PV is connected behind the meter or behind your tenant's meter in this case, they're automatically receiving the utility benefits. And so you'll want to agree on some green lease language that will allow you to recoup some or all of those utility savings from the tenant. In my experience, I've seen an 80-20 or 90-10 split be palatable. So allowing your tenant to keep 10 to 20% of the savings while you as the owner recoup 80 to 90%, contributing to your payback on the investment. Additionally, just again, based on where you're located, some utilities and municipalities will have their own incentives or rebates. So for example, here in Colorado, Xcel Energy will pay 3.5 to 4 cents per kilowatt hour for the solar generated by its customers. And that's on top of the utility savings. And what this does is it allows Xcel to claim the environmental attributes of the system. In other words, they're paying for the RECs, the renewable energy credits. Other utilities might have upfront rebates based on your system size, and other utilities may have no such program at all. And similar with city and state incentives. So again, check with your local contractor to find out what's available in your area. And then lastly, increased property value. So as a result of reducing your OPEX and possibly generating income through those incentives, you will increase the property's net operating income and therefore property value. And we will go through in the case study some of the numbers so you can get a better sense of what a project entails. So while the financial benefits are typically going to be the driving or deciding factor on whether to invest in solar or not, there are some less quantifiable benefits that might have, different levels of importance to each of you. So first, turning an otherwise sunken expense into an asset. A lot of people say that the only certainty in life is death and taxes, and I would argue that utility costs are also part of that. So take that expense, invest it in an asset that allows you to control your utility costs for, the next 3 decades. The next one is becoming quite common here in Colorado. We have new state building performance standards that require property owners of a certain size to choose a compliance path that might include efficiency, electrification, and on or offsite solar, excuse me. And we also have municipalities like Boulder and Denver and Golden that have their own rules, and solar can help you achieve some of these code requirements. And then in addition to those external factors, some companies may have their own internal ESG goals or want to be LEED certified, and solar can help you meet those as well. If you lease your property, you might be particularly interested in how solar can kind of set you out in the market, maybe attract values-aligned tenants, customers, or investors, and just generally create a positive marketing story. And then lastly, investing in this type of energy infrastructure supports local job creation in your community. So now we're going to look at a case study, again, so we can put some numbers to the discussion. We completed a solar project for this industrial warehouse space in Denver a few years back. The facility is 112,000 square feet, but we didn't need to utilize the whole roof because it's a warehouse space, so they have lower usage than you might see in manufacturing, for example. But any PV system will be designed and tailored to your unique utility usage and your goals. So this is a 170 kilowatt DC system. That's simply the nameplate rating of the system. If you recalled, we talked about AC capacity on a previous slide. So just to clarify, DC capacity is the number of modules or panels times their wattage divided by 1,000. And this is just how you will hear the industry refer to system size. But really, what is more important is going to be the system's output, which are kilowatt hours of electricity. And so this system produces about 244,000 kilowatt hours in a year and cost $360,000. So the owner is recouping that $360,000 investment in 4 ways. You can see $229,000 are being recouped in tax benefits through that 30% tax credit and depreciation. $878,000 will be saved on their utilities over 30 years, and $174,000 in the utility incentive payments. So in total, the system is providing about $1.2 million during its 30-year estimated useful life. So that translates to the following investment metrics, including a 6-year break-even and a 13% IRR. I will say here in Colorado, a 6 to 9-year break-even and a 10 to 13% IRR is typical. Again, your return is going to depend pretty heavily based on the utility rates and incentives in your area. I also would like to point out these metrics are also inclusive of the expenses that come with a solar system. So we don't just want to look at the financial benefits, but we also need to account for long-term operations and maintenance, insurance to cover the asset, and business personal property tax expenses over time. And so when everything is accounted for, this owner will have recouped their $360,000 investment and be $708,000 cash flow positive in year 30. So moving to the impact on property value. So this facility's net operating income is estimated to increase by $22,000 in year 1, and that includes the utility savings and income minus the expenses. So at a 6% capitalization rate, that will translate to an increased property value of $370,000, which is about the same that the owner paid for the system. This increase can be monetized, of course, through the sale of the building or as a cash out refinance scenario. And I also want to note, so this property value increase is not included in the investment metrics on the previous slide. So I hope that was helpful in painting a picture and understanding how solar can benefit industrial properties. And I will now pass it off to our next presenter, Drew, to talk through storage. Thank you, everyone.
Thanks so much, Rachel. And give me just a sec here. I'm going to go ahead and take control of the presentation myself. All right, so with that, we will transition to looking at how can solar, PV, and battery energy storage systems help industrial customers. So similar to Rachel's presentation, but talking about how things change a little bit when we add batteries to the mix and what they can do for your facility. Just quick introductions. As Alex mentioned, I'm the managing director of PowerSwitch. PowerSwitch is an energy storage advisory firm. We provide consulting services to developers of storage systems, to customers who are installing batteries, and even utilities and financiers of those types of projects. We do training seminars similar to this, as well as doing independent engineering and owner's engineering work in the energy storage space. Just a quick shameless plug for the book. As Alex mentioned earlier this year, I was one of the co-authors on the BESS book. It's focused on the utility scale battery energy storage space, but runs through everything from the technology all the way to the applications and the finance of those projects, and it is available on Amazon. I know today's focus is on industrial systems, but I would say 70 to 80% of what's in the book still applies to those types of systems. Quickly to run through what I'm going to cover today. So I know that battery technology isn't quite as familiar as solar, so I'm going to run through some of the key aspects of that technology and how those technologies are built up into the products that form part of the projects that would help generate cost savings. We're going to talk through some of the most popular architectures, so the ways that the systems of batteries are put together with solar, talk to some of the value propositions for these types of installations. And as did Rachel, we're going to talk through a case study of a large distribution center in California that put in a solar and battery system. So firstly, a bit about the basics of what's going on inside of a lithium-ion battery. I don't want to get too in the weeds, but it is a form of chemical energy storage. So within a battery, we're having all this interaction of lithium ions. There's an anode and a cathode of a battery, so a positive and a negative, just like in any other battery. However, the difference between, say, a lead acid battery, which is a battery you would have in your car, and a lithium ion is you have all these lattice formed of lithium ions, and those lattices are filled up as the battery is charged and discharged. This graphic shows here on one side you have your anode and the other side your cathode. And when you're charging, it's going in one direction, discharging, it's going in the other direction. This reaction is the same in the battery that might be in your iPhone or Android phone. It's the same in an EV, electric vehicle, and it's the same in stationary energy storage, which is what we're talking about today. And in a minute, we'll see an example of some of the products that are built up using this technology. The leading chemistry of lithium ion that's used in the industry is lithium iron phosphate, commonly called LFP. That's to differentiate from other types of lithium ions, such as NMC or NCA. Those are chemistries that are more commonly used in electric vehicles, where you have a high power requirement. Lithium iron phosphate is more common in the stationary market, everything from, say, a Tesla Powerwall you might see in a garage, up to the really big containerized utility scale systems are all moving toward that LFP chemistry. Just a few quick milestones of the progress in the industry of lithium ion. The main reason that, say, 10 or 15 years ago, you didn't hear much about lithium ion, and now you hear all kinds of news articles about it, is the falling costs. Costs has come way down from about 15 years ago. It was about $1,000 per kilowatt hour. Just for reference, a kilowatt hour is about the size of the energy in a traditional gas car battery. And today we're under $200 a kilowatt hour. So a huge decrease in price. Also for reference, say a typical garage installed residential system might have anywhere from 13 to 14 kilowatt hours in it. Density has gotten a lot better. So the same size of energy storage cell 10 years ago has gotten much better. About just as cost has come down, the density has gone down. That's what's enabled cars to become faster and smaller. And also energy storage containers used to hold less energy. Now they hold quite a bit more. And lastly, the durability. It used to be that 3,000 cycles, so roughly one charge and discharge per day over 10 years was the standard. Now we're seeing warranties of 10,000 or even more cycles and a 20-year warranty on some of the systems. And just lastly, to comment on that chart you see in the lower right corner, This is both current installations. You can see that they've really ramped up very quickly from 2016 to today and projected to go even further as the technology becomes cheaper and more prevalent. Just a quick look at how we go from the cell of a battery. So that's roughly the size of a shoebox, holding from 300 up to 1200 watt hours. So just over 1 kilowatt hour of energy. Moving up to the rack level, something around the size of a phone booth. If anybody remembers what one of those looks like, it's somewhere from 100 to 300 kilowatt hours in that size. And then moving up to the enclosure level, this would be more for utility scale, but the 20-foot shipping containers now are holding up to 7 megawatt hours, equivalent to 7,000 kilowatt hours. On the commercial and industrial scale, which is what we're talking about today, most of the products are closer to the rack level, that 100 to 300 kilowatt hours. One critical aspect of batteries is the power conversion system, or PCS. Rachel mentioned inverters in the system, and every solar plant has to have an inverter to convert the DC power production into AC power that our grid runs on. And similarly, batteries need that same technology because batteries are DC and they want to feed power to an AC grid. The big difference is that where solar is always going one way, meaning that the solar panels are generating DC energy and putting that energy onto the AC grid, batteries have to go in both directions. They have to be charging, meaning pulling power from the grid and going into the battery, and discharging power from the battery into the grid. And so they have a bidirectional inverter, also known as a PCS. At a high level, here is a typical installation of a commercial industrial solar plus storage system. You can see on the left here, we have the batteries on the top. It consists of several units all linked together. On the bottom, we have the solar and the inverter. Those are electrically coupled, and then they will typically run through some sort of AC power distribution system. This could either plug into an existing panel or might be a new panel that gets added to the facility. On the top, you can see the elements of a control system. Every battery system has to have some kind of control system to tell it when to discharge the energy, when to charge. And you can see on the right-hand side, it's connected both to the loads, so the existing facility load, as well as to the power grid. We're going to talk a little bit about some use cases that involve islanding, meaning being able to disconnect from the grid. But for most of the industrial customers we work with, the battery is designed to work with the grid as opposed to islanding itself from the grid. Here's just a quick look at some of the products that you'd see in the C&I space. On the left, we have a Canadian Solar C&I product. We have CPS, or Chint Power Systems, is second there. SunGrow is the biggest inverter manufacturer in the world, and they have a number of solutions for energy storage. And on the right, we have a newer company called Alpha ESS. All of these are somewhere on the order of 2 to 3 meters tall by somewhere around a meter wide and a meter long, just to give you an idea of the size. Although most of them are designed to be modular, so you can install many of these next to each other in the field. A quick note on some of the key terms that you hear when you talk about architectures, so the way the system is put together. Front of meter refers to systems that are connected directly to the power grid via their own meter. So they still have a meter that's connecting them to the grid, but they are not connected together with the load. Whereas behind the meter, or BTM systems, are connected together with the load. So since we're talking about industrial systems, most of those are behind the meter, meaning that you're installing a battery on the site of the facility in order to lower your costs of energy, or it could provide some other important services to the facility. Whereas front of meter tend to be larger installations, such as utility scale battery projects. When I say utility scale, I'm talking of, say, the equivalent of several football fields full of energy storage containers. So those are just two common terms, front of meter and behind the meter. Secondly, you may hear a lot about DC coupled or AC coupled solar plus storage. That refers to whether the battery and the solar have their own inverters. That would be AC coupled. So you can see on the right here, we have that red box, which is the solar inverter, and the white box, which is the battery inverter. And there's another way to hook it up, which is called DC couple, where you have a single inverter that's fed both by the solar and the battery. I think there's not quite enough time to get into the subtleties of the differences there. But in general, the more common architecture today is AC coupled, meaning that your battery has its own inverter, the solar has their own inverter. Even though that means there's two inverters, it gives the system more versatility and allows it to provide some different functions. We're going to move on now to talk about some of the use cases that batteries and solar can be used for in order to save money for your facility. So the most common use case is something called peak shaving. So as most of you know, industrial facilities get charged not only for the energy they consume, but also for the power they consume in the form of demand charges. And I know it varies from region to region, utility to utility, but many industrial customers can have a huge burden from those demand charges, meaning that if they use the same amount of power at one time of the day versus another time, they can either save a lot of money if they avoid the peak times or incur a lot of charges if they are using power during those peak times. So while Rachel went over some of the benefits from solar, and if you look at this graph, this white line in the middle shows more or less the amount of solar you'll get out, obviously peaking in the middle of the day and no generation at night. And if we compare that to the other curve, in this we have a twin peak load, meaning there's a load that peaks in the morning, goes down in the middle of the day, and then peaks again in the evening. That's common of some industrial loads as well as some grids. You can see that they're sort of mismatched. We have a lot of power production in the middle of the day when we don't have as much load. And then when we have the load in the evenings and the mornings, we don't have as much production. So enter the battery. The battery system can provide a big benefit by charging up with the energy when it's plentiful in the middle of the day and discharging in those times when the energy is more expensive or there's higher demand. So typically when the grid has these spikes, that's when the demand charges are going to be highest. Some markets in the country also have time of use rates, meaning the actual kilowatt hour price goes up and down. I live in Portland, Oregon, and I have an EV, and so I figured out how to get it to charge in the evenings when the power is, the energy is slightly cheaper. Same idea, you're having the battery charge in the daytime, discharge when the power is more expensive, and of course you're saving on your utility bill because of that. I would say this is by far the most common use case for energy storage systems, especially for industrial customers, just because we know that demand charges especially are a really big contributor to utility bills. But I did want to go over some of the other alternate use cases that batteries can be employed to save money for industrial customers. The first would be a microgrid configuration. It can also be referred to as resiliency. And that is when a system is able to become its own microgrid if the grid were to go down. I know up in the Pacific Northwest, we've gotten hit with this bomb cyclone, which caused a lot of power outages up in Washington State. And because of that, there's a lot of customers that don't have power. If you were to have a battery, of course, you're able to island and become your own power source. And that is really attractive. The downside of that is it's generally quite expensive to become a microgrid or an islanded industrial facility. Generally, the size of the system would have to be quite large. It's a big capital expense. However, there are some customers where it makes sense. For example, mining is one where they tend to be in very remote sites. Maybe they're not even connected to the grid or have their own generation. And so that resiliency use case can be really attractive. Another alternate use case is not only when the power goes down, you may want to have backup supply, but you may want to have a bumpless transition. Bumpless refers to the fact that the grid goes out and then your industrial facility would never notice the difference, that you would just continue with the same power and be disconnected to the grid. That is what is commonly referred to as an uninterruptible power supply, or UPS. You may see it on a small scale for a server or a computer. But it can be used on a large scale. But again, similar to microgrids, the problem is that those systems tend to be quite expensive. Another issue is that a lot of utility grids don't like systems that come online that quickly because it presents a safety risk for their grid operators. So again, there may be specialized applications where bumpless transition is sought after, but it is actually pretty rare in the field we would see that. Lastly, I wanted to touch on there's ancillary service markets. So that is things that the utility company needs in order to run the grid, such as frequency regulation, which is sort of a fine balancing of the power grid. Some industrial customers have a battery that helps them manage their load, but that battery also participates in some of these markets. Those tend to be really large systems. Usually you have to be at least a megawatt in order to go onto the grid and do those services. But for really large customers, it is an option, and it can even further increase the economics of a battery storage project. So with that, I'll turn to the case study. I am presenting here on a 1 million square foot distribution center for Costco. I think most of us have probably been to a Costco. I think each Costco almost looks like its own distribution center. So you can imagine the size of a Costco distribution center. This is located in Mira Loma, California, down in Southern California. You can see on the map there. I just did a quick check of what the average the average industrial rate is for energy. It's about 17.4 cents per kilowatt hour. There's a bit of a typo there. It says kilowatt, that's kilowatt hour pricing. And then there's also demand charges on top of that. So there's a strong use case here where that facility really saw that they were having massive energy bills, and Costco wanted to do a demonstration on this facility to see if it would be profitable for their other distribution centers around the country, or potentially even the Costco stores themselves. One of the big drivers in this case was EV charging. They have a big fleet of electric vehicles, and they realized that if they were to plug in all the electric vehicles they wanted at one time, that would actually pull more power than their grid would allow for. And so they considered a battery energy storage system that would allow them to store the power in the batteries. And so when all the EVs were charging, it could pull off of that battery instead of going to the grid, and help them avoid some really large costs associated with increasing the power supply to the business. So they installed 80 kilowatts of DC coupled solar energy on the roof. They put in place 480 kilowatt hours, so almost half a megawatt hour of battery system. And they also have 22 kilowatts DC fast charger. So relative to the size that a facility like this could support, I know Rachel mentioned that you can have a much larger facility. They did a small portion, but it was also a trial, and they have said that if it's successful, they really want to replicate this on a much larger scale. So you can see here some pictures of what the installation looked like. That's actually the charging station on the lower half of the screen. That's a big battery that's under part of the solar canopy. Part of this solar was installed as rooftop canopies, and another part was installed actually on the distribution center roof. The financial benefits are not totally public, so I can't go into the same depth that Rachel went into, but more or less the system cost around $450,000 just using current rates. But that's outside of the EV charging, because I wanted to just talk about the solar and the storage. As Rachel mentioned, all those ITC benefits, the investment tax credit benefits, as well as California incentives, applied to this project. So they ended up saving Costco a lot of money on the installation that they got back on their taxes. They have stated that they have almost 12,000 hours of off-grid fleet charging as a result of this, meaning that their system is able to pull that energy that came from the solar, stored in the batteries, and then went into their electric vehicles, avoiding that upgrade to the power system, and also saving energy because the energy from the solar was much cheaper than that 17 cents a kilowatt hour. And they have already announced that this project was a success. We don't know the exact rate of return, but suffice it to say that based on these results, Costco would not go ahead with this unless they really had a strong financial case to be made, that putting these in place allows them to expand their EV fleets, which would save on fuel, reduce their energy demand because they're pulling from solar, and then those batteries help them avoid the large demand charges. So that's a bit about that case study for an industrial customer. Just 4 takeaways that I have here summarizing some of the presentation. First of all, the technology itself and the cost of that tech has really changed a lot in recent years, making batteries more and more a viable solution for industrial customers. Secondly, batteries, while they're useful on their own, they also, when coupled with solar, really make a great case for not only having that cheap energy, but moving that energy around to reduce both demand charges and energy charges. Lastly, the feasibility of any battery project really is a function of the tariff. In the Pacific Northwest, we're happy to have lower utility rates for energy, but for industrial customers still have those demand charges. You really have to look into what those charges are and what the power and energy charges are to determine what the financial effect of the system is going to be. And lastly, that peak shaving is the main use case, but there are many different use cases that batteries can be used for industrial customer. Really depends on your load, on the region you're in, and as well as some of those incentives that are available in that region. That concludes the presentation. Thank you so much for attending. If you do have any additional follow-up questions, there's my email. Happy to chat more about them. And with that, I will turn it back over to Alex for the Q&A session of today's presentation.
Thank you so much, Drew. Really appreciate your presentation. Folks, at this point, I would encourage everyone to utilize the Q&A section to enter any questions you have. And then what we're going to do is have Drew and Rachel, if you'll look at, I'm going to read these out and then people can answer them as they see appropriate. I think the first couple questions actually are probably targeted at Drew. So with that, we'll start with Glenn Anderson's question. Glenn Anderson asks, what barriers do you see for sodium sulfide batteries to gaining market share?
Yeah, great question, Glenn. So as you saw, my presentation focused really exclusively on lithium-ion batteries, but that is one type of battery. There's a whole bunch of different chemistries. So within lithium-ion, there's sort of flavors of lithium-ion, and then outside of lithium-ion, there's a whole bunch of other types of chemistries. One of them is that I think it's sodium sulfur battery that you referenced, but there's a whole bunch of different chemistries like iron air, a whole bunch of other options out there. I talk about lithium-ion because if you look on a commercial scale of how they're getting deployed, lithium-ion now is about, I'd say, 98 or 99% of all deployments. The costs have come way down. The quality has gone up. The warranties have gotten really a lot longer. If we were to look 5 or 10 years from now, I think there probably will be some other chemistries, but lithium-ion really is way out ahead of all these others. So they're sort of still in closer to an R&D or a prototyping phase, whereas lithium-ion was there maybe 5 or 10 years ago. So I think those are the biggest barriers, is that just lithium has a real strong establishment right now. But over time, I do think that all the major lithium-ion companies are doing research on other types. There's been a lot of talk of sodium. Sodium is another metal that could be used in replacement of lithium. It's safer. So I think they're coming, but I think the big difficulty is lithium-ion just has a big head start.
Thank you, Drew. I appreciate that. I'm gonna pass one to Rachel on this next one here. So Rachel, this next question that came in is, what is the primary motivation for your customers for adding solar? Is it primarily economic, resilience, decarbonization, or some other justification?
Sure. So I would say by and large, in our experience, the driving factor is going to be economic, and does it make sense for the bottom line? I would say there are certainly other reasons, but at the end of the day, it's got to make financial sense. Secondary, I would say, at least in Colorado in particular, because of recent building performance standards on the state and municipal level, that may shift it to where that becomes more of the initial motivation, and then the economics back up the decision. So it's a combination, but primarily economic.
Okay, great. So this is another one that came up, and I guess this one is probably directed at Drew. Is resiliency an all or nothing prospect to achieve islanding, or do sites ever utilize BESS as a very large UPS dedicated to, say, a sensitive, critical process?
That's a great question. Yeah, I think I was really referring to that islanding as more of a facility-wide, but you're absolutely right that a battery could be applied to, say, one certain area. I think when we see UPS in a traditional sense, it might be on, say, one server or one computer or area of a system. But as batteries have gotten larger, there is a great use case to be made for ways that the system could support a larger area or a larger process. I know, for example, the Megapack, which is Tesla's utility scale offering, a single storage container goes up to about 4,000 kilowatt hours or 4 megawatt hours in around a 20-foot shipping container. That they have actively marketed that to mining sites, to other industrial customers. And I think you can either go the same way with a residential system, can be what they call whole home backup. So your entire house is supported, or partial home, where you'd say you'd have, let's say, a freezer and your internet or whatever other critical loads. You could put that on the battery. Similarly, an industrial site could be the same way, where they may say, okay, we've got this one motor or server or whatever area of the system that's very critical, and because of that, we can back it up. So yes, from a resiliency point of view, you could set it up as that bumpless transition. However, I would say that when you get to a certain scale, you still have some of those concerns that if you're pulling power and you want to form the grid, so when you have a grid outage happen, you want to form the grid very quickly, you still may run into those concerns from the utility, because they're always afraid of a large system like that backfeeding the grid and potentially creating a safety hazard, whether it's part of the site or the entire site.
Okay, great. Here's one from Ken Garner, and I think he's referring to the Costco case study here. He said, on DC fast charger, why only 22 kilowatts and why only one?
Yeah, that's a good question. I saw that on there, and I jumped on the case study just to look into that. I think what they actually did was they had 4 regions around the site, and so it's actually 4 22 kilowatt fast chargers, one for each of those 4 regions. So in aggregate, it would actually be 88 kilowatts. But still, it did strike me as a little small. Also, for anyone who knows EVs, like some of the fast chargers now can go up to like 100 or 200 kilowatts. I don't know their motivations, why they would go slower. I do know that if you consistently charge EVs at really high powers, that can be detrimental to the battery. So, for someone like Costco, where they're really concerned with, long operations of their fleet, perhaps they determined that having not the highest powered charger was better for that fleet in the long run. But again, it was also a pilot project, so it could be that based on what they've learned, they may be able to scale this up, either bigger individual chargers or banks of many different chargers as their electric fleet increases.
Okay, so this next question, I guess this could probably be for either Rachel or Drew, so maybe I'll let you both take a stab at this. And maybe Rachel, you can go first. When you convert from solar to battery to grid, there are losses. Are the losses significantly different from those of a utility generating power? Maybe you can speak to the inverter losses and things like that.
Sure. So I don't think I can answer the question directly, so I may pass it to Drew or get back to the person. What I can say, at least, is when we are modeling the output of our systems, our design engineers are accounting for these types of losses that happen in transfer of power. So that's included in the production modeling. I can't definitively speak as to whether those losses would be different from the utility, with the exception, when power is traveling long distances, you'll have greater losses than when power is traveling short distances. So that could be one thing to consider when solar and batteries are right there on your site. You'll have less losses going to the building as opposed to pulling power from a distant facility.
Thank you, Rachel.
Yeah, I think that captured it pretty well. The only thing I would add is that you are operating typically at industrial voltages. So it might be, say, 480 volts, or maybe you have a site that has medium voltage. So usually there will be, although there's smaller distances, having generation very close to where your load is. It's short distances, but it's higher losses because the voltages are lower. That's one thing that's driving why we've seen, say, battery products and PV get up higher. Now, a lot of the bigger systems will operate on 1,000 or 1,500 volts because all that helps to reduce losses in the wires. The individual components have losses that are sort of unavoidable, but those have all gotten a lot better Nowadays, inverters typically are, say, 98 or even 99% efficient, meaning you're only losing 1 to 2% of the power as you go through that inverter. And similarly, batteries, that's another area that they've gotten a lot better in. If you look at the round trip efficiency, or RTE, of a battery, even 10 years ago, it was, say, 82, 85%. Most of the batteries now are up to about 95%, meaning if you put 100 kilowatt hours in, you get 95 kilowatt hours out. So always some losses, but the losses are getting less as the technology evolves.
Excellent. Here we have a question from Bill Alfhouse, which says, EV battery tech is rapidly innovating. Both China and Australia have launched vehicle-to-grid at national scale. Will employee EVs in the vehicle-to-grid become the on-site storage in the future? Free cars for employees? Maybe one for Drew.
Yeah. So for those who don't know, vehicle-to-grid, or V2G, is a technology where most of our electric vehicles are thought of as one way, meaning they pull power from the grid, put it into the vehicle. But more and more cars now are being built in ways that the battery can power the grid, either the grid as a whole and putting power out to the main grid, or even just to say a home backup. To use an example, the F-150 Lightning EV pickup has an option where you can actually have the vehicle wired to support your whole home, which if it's fully charged, it could be like 1 or 2 weeks you could be running on your F-150 if it was a big long outage. So there has been a lot of thought that as the grid evolves, we'll see more and more vehicles that are serving bidirectionally, and that charging will be something that really can help expand the grid. Tesla recently did what they call a virtual power plant, which is many power walls, so not EVs, but residential batteries all hooked together to discharge over 100 megawatts into the California grid, so the equivalent of a really pretty big power plant. And so a lot of folks think that EVs will be part of the future grid through this V2G program. And you're correct that China and Australia, but also in the US, there have been pilots of V2G. It's just, I think, a really difficult problem to solve. There's a lot of hardware, software. EVs are not like batteries that are constantly firmly connected. You have a plug that's being plugged and unplugged. You don't know where they're going to be. So I do think it's the future, and it certainly could help big fleets of vehicles or incentivize their employees. But I think it has a ways to go for commercialization, even in those markets where they've been a little more aggressive with their pilot projects.
Okay, let's take, looking at the time here, let's take maybe 2 more questions, and then we'll wrap it up for today. So Doug posted one that says, question for either or both. Are there any new technologies coming in the near term, more efficient panels or better batteries? Maybe we can give Rachel and Drew each a minute. You want to start, Rachel?
Sure. So first and foremost, I would say yes, the panels do and have become incrementally more efficient over time. Maybe 7 years ago, they were at 17% efficiency, and today we're looking at 21% efficiency. So that is certainly something we expect to continue. They also get higher wattage as time goes on, but one caveat to that is, while a couple of years ago, maybe we were integrating 400-watt modules and now they're 550s, they also come in a larger format, so they're bigger. Commercial modules these days we're speccing are about the size of a piece of plywood. So they're getting higher wattage, but they're also taking up a larger footprint. Something else I'll share here that isn't necessarily technology that's coming because it's already here, but as of recently would be bifacial modules. So panels that have the ability to generate electricity from light that hits the backside. I think there is a lower benefit on a rooftop system where the panels are placed, pretty closely to the roof and not much light can get back there. But on something like a ground mount or a carport where the back of the modules are exposed, we are seeing cases of increased production as a result of that technology.
On the battery front, there's a number of different exciting advancements. I think we already touched on a few of them, those being chemistry. There's some really interesting new promising chemistries, such as that iron air or the sodium sulfur battery that someone mentioned. Continually, a lot of R&D going into that. I think sodium is seen right now as kind of the leading potential lithium killer, but it remains to be seen if they'll be able to scale it up the way lithium is. One other thing that we haven't talked about is a solid state battery. So most of these batteries still have a form of electrolyte, which is a liquid used to bring the lithium ions back and forth. And a solid state battery would be one where there's a solid instead of a liquid. And there's a number of different efficiency gains that come from that. And we're just starting to see those cells go into production for electric vehicles. So I think they're still several years out from actually being on the road and eventually being in homes. But that would really herald a new era where we'd be talking about vehicles with, say, 1,000-mile range instead of a 200, 300, 400-mile range, and similar increases in density and performance for stationary batteries. So lots of great stuff happening.
Thank you, Drew. And I think let's do this last one here. How do you anticipate the election results may impact the future of solar tax credits?
Timely question that many folks are talking about right now. I think as what happens with many changes in administration, the new one may look to change things of the past and, of course, implement their own new legislation. This is really pretty fresh, so I think the market is still trying to understand exactly what we might expect. I think we believe that there will likely be changes to the Inflation Reduction Act. We think a full repeal would be very challenging and unlikely. Both blue and red states benefit pretty significantly from the funds available as part of the IRA. And so our hope and speculation is that it largely stays intact, including that base 30% tax credit. Currently, it's set to sunset in 2032. There could perhaps be a shorter runway of that tax credit, and possibly some threat to the tax credit adders. I think in the near term, solar is probably going to have a very big 2025 as folks look to get their projects secured before there are any tax law changes, if there are any. So we'll really know more in the next, 6 to 9 months. But that's what we're thinking and considering right now.
I think Rachel covered it really well. The only thing I would add there is that we don't know exactly where things will go, but the reason that all these technologies have been the preferred choice for new power plants coming online, both utility scale and industrial, is because they're cheap. Solar especially has gotten a lot cheaper, so have batteries. And even if the ITC were to go away entirely, which I don't think it will, and I hope it doesn't, there would still be a lot of projects that are great cases for solar, for batteries. And as the tech evolves, those would be more and more. It just won't have the wind at its back that the ITC was providing, but it still will be coming.
Awesome. Well, I want to just extend a big thank you to Rachel and Drew for sharing your expertise today. And last but not least, I want to remind everybody that the On-Site Energy Tap is here to help your site dive in and explore these technologies for your site. And all industrial sites in the U.S. are pretty much eligible to get a free technical screening through this program for your site that is specific to your site. So encourage you to reach out to us or reach out to any TAP that covers your territory and pursue a technical screening through that TAP. Thanks again, everybody, for your attention and your great questions, and I hope you have a great, wonderful rest of your day. Thank you.